This is a simulation of the operation of a step-down control transformer. It uses two electromagnetic coils, a primary and a secondary, to step down the voltage. Note that the number of turns on the primary coil is greater than the number of turns on the secondary coil. This is the case for all step-down transformers. Voltmeters are connected to the primary input and secondary output and indicate the change in voltage levels. When the simulation is turned on, the transformer steps the primary voltage down from 120 volts to a secondary voltage of 24 volts in direct proportion to the 5:1 turns ratio. This is a simulation of the operation of an electromagnetic control relay. The input control circuit has been pre-connected and consists of the DC power source, control switch, and the electromagnetic relay coil connected in series. The output load circuit is shown being connected with the AC power source, normally open relay contact, and fan blower motor in series. When the switch is closed, the relay coil is energized, closing its normally open contact to turn the fan on. The fan will remain on as long as the switch is closed and the coil is energized. When the switch is open, the coil is de-energized to return the contact to its normally open position and turn the fan off. This is a simulation of the transmission of electric power at a low voltage level. The circuit simulates the transmission of 10,000 watts of power at the 100 volt level. The voltage at the generating plant and consumer load are both 100 volts. The current in the two line conductors is calculated by dividing the power by the voltage. In this case, 10,000 watts divided by 100 volts equals 100 amps. This is a simulation of the transmission of electric power at a high voltage level. This circuit simulates the transmission of 10,000 watts of power at the 10,000 volt level. The voltage at the generating plant and consumer load are both 100 volts. The generating plant step-up transformer is used to raise the voltage to 10,000 volts for transmission purposes. The consumer step-down transformer is used to lower the voltage to 100 volts for consumer purposes. The current in the two line conductors is calculated by dividing the power by the voltage. In this case, 10,000 watts divided by 10,000 volts equals only 1 amp. The consumer still utilizes 100 amps at 100 volts. This circuit simulates the connection of a wattmeter used to measure power. The power consumed by the heater is first to be calculated, then this calculation verified measuring the power of the wattmeter. Heater power is calculated by multiplying the voltage by the current. In this case, 120 volts times 8 amps equals 960 watts. Connecting the wattmeter into the circuit requires that the wattmeter current leads be connected in series with the heater, and the wattmeter voltage leads be connected in parallel with the heater. Once the wattmeter is connected, the simulation is turned on to verify your calculations. This circuit simulates the calculation of current flow in a circuit based on the wattage divided by the voltage and its verification with the simulation. Expected current flow equals 150 watts divided by 120 volts, which equals 1.25 amps. The amp meter is connected and the simulation is turned on to verify the current calculation. This simulates the calculation of power in a circuit based on current and resistance. Expected wattage equals I squared times R. For 0.5 amps of current, power equals 0.5 amps times 0.5 amps times 100 ohms equals 25 watts. For double the current, or 1 amp of current power, equals 1 amp times 1 amps times 100 volts, or 100 watts. Note when the current is doubled, you get 4 times the power. This circuit simulates the calculation of power to a heater when voltage applied is below its rated value. The resistance of the heater element remains the same at all times and is calculated based on the rated voltage and current values. For this heater element, R equals 230 volts divided by 5 amps, which equals 46 ohms. When operated at 215 volts instead of 230 volts, I equals 215 volts divided by 46 ohms, or 4.67 amps. Therefore, when operated at 215 volts, power equals 215 volts times 4.67 amps, or 1004 watts, compared to its rated wattage of 1150 watts. These two conditions are demonstrated by turning the simulation on and observing the 2 amp meter and watt meter readings.